And today I'll talk to you about work I've been doing to optimize the performance of KVM on ARM. Virtual machines are defined as being efficient, isolated duplicates of the real machine. Back in the 70s, I hope it can Goldberg. And this talk is very much about the efficiency part. So, quick reminder, or maybe you don't know what virtualization is. Normally we run an operating system directly on the hardware. We run applications on top. With virtual machines, we add another layer of software called the hypervisor in between the hardware and the operating system, which creates an abstraction of multiple isolated virtual machines and partitions the real hardware. And that's really great, but it comes at a cost, and that cost is performance. There are two fundamentally different types of hypervisor designs. There's type 1 hypervisors, or standalone hypervisors, which run an independent piece of software directly on the hardware and runs operating systems on top. The advantage of that design is that the hypervisor is really small. The disadvantage is that you have to re-implement things like a scheduler, memory management, device drivers, and platform support. So a popular alternative is something called type 2, or hosted hypervisors. And here you take an existing operating system and you add hypervisor functionality to it. The benefit of a hosted hypervisor design is that you can reuse all of the OS's functionality, like a scheduler, memory allocator, and device support. Like deployment becomes much, much easier. The downside is that your trusted computing base is potentially much, much larger than your type 1 hypervisor. An example of a type 1 hypervisor is Zen, and an example of a type 2 hypervisor is KVM. Although Zen relies on DOM0 for hardware support to avoid re-implementing all device drivers, so that discussion becomes a little bit more complicated. The problem with ARM and type 2 hypervisors is that the ARM hardware support for virtualization was specifically designed for type 1 hypervisors like Zen. So let's quickly refresh our memories about the ARM virtualization extensions. So that's the ARM hardware support for virtualization, which were introduced really because the ARM architecture is not virtualizable by its classical definition. The ARM protection mechanism uses two CPU modes, EL0 and EL1, to run user space in the kernel. The virtualization extensions add a new mode, EL2, specifically designed to run hypervisors. EL2 is designed to be as simple as possible to run hypervisors and not full operating systems. Okay, so really important distinction. And that works really great for something like Zen, where you run all the hypervisor in EL2 and you run your VMs on top. But not so much for KVM, right? Because Linux is written to run in EL1, right? But you need to run some sort of software in EL2 to run VMs, and you can't easily run Linux in EL2. So how do you run KVM? The answer is we do something called split mode virtualization, where we split the execution of KVM across both EL1 and EL2. But it has the very unfortunate side effect of having to multiplex the EL1 CPU mode between the host kernel and the VM kernel. And you have to do that in software. So if we consider, for example, a hypercall from a VM that runs to the hypervisor, what you have to do is you issue a hypercall instruction from the VM kernel, which traps the part of KVM that runs in EL2, which switches all of your EL1 execution state around, and then returns back into your hypervisor running in EL1. You then handle the hypercall, but to return to the VM, you have to make another hypercall to enter the EL2 again, switch all of that EL1 state around again, and then finally return into the VM. What if we could do that instead? Right, wouldn't that be nice? Right? The benefit is obviously we no longer multiplex EL1 between two kernels. And if we need to handle a trap for a hypercall, we just do a hypercall and we return, and that's it. The question is, how do we then run Linux and KVM in EL2? Well, that's where ARM v8.1 VHE comes in. VHE is short for the Virtualization Host Extensions, and they support running unmodified operating systems in EL2, which were written to run in EL1 really, and running applications in EL0 on top without using EL1 at all. In some more details, VHE actually gives you 5 things, and I'm going to go through each one. So first, VHE is backwards compatible. So there's a new bit in the hypervisor control register, the E2H bit, which completely enables or disables VHE. So, for example, Zen would disable VHE and would work on an 8.1 hardware exactly like it does on an 8.0 hardware, no change. The second thing that VHE gives you is, remember I said that EL2 was designed to be limited compared to EL1 to only have the functionalities required to run hypervisors and not full operating systems? VHE changes that. So any functionality you had in EL1 before, now you have an equivalent piece of functionality in EL2. So you get new registers. You get an additional timer. EL1 had a virtual and a physical timer. EL2 only had a physical timer. Now you get a new EL2 timer. The third thing it does is it takes an existing feature of the architecture called GG, or Trap General Exceptions, which is a bit that when it's set will route all exceptions to EL2. But that original feature was really designed to run bare metal applications in EL0 on top of a hypervisor running in EL2. To make it easier for hypervisor developers to run those applications, it disabled the stage 1 MMU in EL0. The idea being that the hypervisor didn't have to worry about virtual addresses in EL0, and those applications could just use physical addresses. So if we wanted to use this feature to support this scenario, we would get no virtual addresses in EL0. That obviously doesn't work with applications on Linux. So with VHE, you no longer disable the stage 1 MMU in EL0. The fourth thing that VHE gives you is that we now get to use the same page table format in EL2 as in EL1. EL2 used to have its own page table format, which was limited compared to EL1. And we only had half the virtual address space available, only a single translation table base register. But now we get a setup that works for both EL0 and EL2 for virtual memory in exactly the same way as EL1. And fifth, and finally, VHE will transparently redirect system register accesses from EL1 registers to EL2 registers. Okay? So assume you have code written to read the TCR EL1 in Linux, right, using the instruction encoding for this instruction, right? When VHE is disabled and you run in EL2, that instruction will do what it always does. It will just read TCR EL1, right, which fits with the instructions assembly logic. If you enable VHE, the hardware using the same instruction encoding when you run EL2 will actually read TCR EL2 for you when you use this same instruction. Okay? That's how an operating system written to run for EL1 can run in EL2 and be controlled in EL2, being completely unmodified. Right? What if you actually did want to read the EL1 register? That's something the hypervisor wants to do when it prepares the VM's execution context. So for that, you get a new instruction, a set of instructions actually, which are the EL12 instructions, which always access the EL1 register. Right? And to make it even more confusing, VHE also changes the bit layouts of some registers. So for example, if you look at CNTK CTL EL1, the instruction to access that register gets redirected into the CNTH CTL EL2, but those two registers have completely different bit layouts. So when you enable VHE, the hardware says, oh, magic, let's just shift the bits around, change their meaning, and add some extra bits on top. Pretty confusing. So if we come back to the legacy KVM ARM design without VHE, right? I said Linux could run in EL2 with VHE without being modified. But that's not true for the hypervisor and for KVM. That has to be actually modified to run VMs. Okay? But the good news is it's pretty simple. All we have to do is we have to change a series of the instructions to use the new EL12 accessor instructions. And we have to change this trap that we used to go from the part of KVM running in EL1 to go to the part running in EL2 to a function call. And then, hallelujah, we run all of KVM ARM in EL2. That's great. So we want to know how that performs, right? But unfortunately, I didn't actually have VHE hardware available when I started this work. So performance evaluations have been done with Linux running in EL2. And I did a talk in Bangkok last year about what we do there. But for the purpose of this talk, I will claim that the performance characteristics of that setup is very close to the same set of hardware, to the same piece of hardware that had VHE. So using Linux running in EL2 on an AMD Seattle V0 with 10 gig Ethernet and using BFI pass-through for all of the workloads with I/O that you're going to see later, we get our results. So this is how a hypercall performs in terms of cycles on non-VHE compared to VHE. So hypercall is an important measurement for virtualization performance in general because it's your base cost of transitioning from the VM to the hypervisor. And that doesn't really contribute to executing your workload. So the more you have to support your VM from your hypervisor, if you have a high transition cost, your overhead is going to be high, likely overall. What we see here is that the benefit of VHE doesn't really look that great. And that's not really surprising, right? Because all we did was we changed the trap to a function call. So sure, around 100 cycles, that's fine. But the problem is that KVM ARM is still designed with this idea of split mode virtualization in mind. So what we really have to do is we have to more substantially redesign all of KVM ARM to take advantage of VHE. So we do a number of tricks. So the first trick is that we no longer save and restore the EL1 state when we move between the VM kernel and the host kernel, because we don't use EL1 for the host environment at all anymore. So we can simply leave it in hardware and move back and forth. The second trick. In the legacy KVM ARM design, we were enabling and disabling virtualization features in every transition between the host kernel and the VM kernel. Why were we doing that? Well, that was because the host kernel, part of the hypervisor, we wanted that to have full access to the underlying hardware. But the VM kernel, also running in EL1, we did not want it to have full access to the hardware. We wanted to limit what it could do. Right? So we did things like enabling traps, setting up stage 2 memory translation to limit which memory it could access when we entered the VM, effectively making the VM kernel less privileged than the host kernel, even though they both run in the same CPU mode. With VHE, we can always leave those features enabled. We just configure the hardware for running VMs once when we boot the system, or when we load the KVM module in the kernel. And then we just leave those configured. And that works because EL2 never uses stage 2 translation. It always has full access to the underlying hardware, no matter how the virtualization extensions are configured. The third optimization is we don't context switch the timer on every transition anymore. Right? So we used to save and restore all of the state of EL1, right, as I said before. And that meant that you didn't actually have your timer state in hardware, but you had to inspect the state of the timer in software on every exit from the VM and determine if the timer was going to fire and inject virtual interrupts. So what we do now is we completely rework that logic to leave the state of the timer in hardware and be able to take interrupts in the hypervisor from the timer and directly from the ISR inject virtual interrupts to the VM. There's a patch set for this on the list with about 20 patches. The fourth optimization is that we move as much work as we can out of the vCPU run loop inside KVM. Right, so KVM works with this notion of a run loop inside the kernel. And what that does is it's a loop which runs as much code as it can from for the VM directly on the CPU, on the hardware. Right? But for each iteration of that loop, if there's a lot of work in each iteration, your performance is likely going to be very bad. Right? And what we had to do before was we had to configure the hardware pretty much in every iteration of that loop. So what we can do is we can move hardware configuration out of the loop into these two hooks called vCPU load and vCPU put. These are hooks that are called whenever you enter the run loop from user space, or if you're preempted in the kernel, we use preempt notifiers to call vCPU put, and then when you're scheduled back in, you call vCPU load. So intuitively, when you're loaded, it means that now we're going to run this vCPU on this physical CPU for a longer amount of time, right? And we try to do the bulk of our work there instead of inside the actual run loop. Note that actually didn't work before VHE, because if you try to configure your hardware in vCPU load, you'd be overriding your own execution state and crash your kernel. The fifth and final optimization is we completely rewrote the part of KVM called the wall switch. So basically what we do now is that in the run loop in the kernel, we evaluate the static key as VHE, and we say if you're a VHE kernel, you're going to run your magic VHE wall switch function, which is a really simple function that just replaces a couple of registers, switches a couple of registers around, and the general purpose registers, and then runs the VM. Where in the legacy case, we're going to call a hypercall into EL2 with a much more complicated wall switch function. And with those things in place, we get some better results. Right? So again, this shows cycles, and the first column here is our legacy KVM ARM design. The second column is KVM ARM designed for VHE and optimized for VHE. And then we show x86 results as a baseline reference. Right? So we actually get a reduction in the hypercall cost by more than 75%. And we are now about half of that of the x86 cost. The other numbers, IO kernel, is the cost of doing I/O for the VM in the host kernel. I/O user is the same, except you do it in the host user space, so in QEMU essentially. And virtual API is the cost of sending an API from one virtual CPU to another. So we see that we get improvement across the board except for I/O user, and we do better than x86 except for I/O user. I/O user is something we already try to avoid heavily with KVM because it's generally slow, also on x86, right? So I'm not too concerned about that number. We also wanted to measure how this actually looks like at a real application level, right? So we ran some popular benchmarks, some typical applications like a web server and a key value store. And this is what it looks like. So these results are normalized to 1 for native performance. So lower here is better, meaning less overhead. The blue bars are our legacy KVM ARM design, and the green bars are KVM ARM designed and optimized for VHE. So here we see a 50% reduction in overhead for network benchmarks in Apache. And we see that the overhead of Memcached gets reduced to about 1/5 of what it was before. These are pretty strong results. So in conclusion, we've optimized and redesigned KVM ARM for VHE. It's a significant amount of work, and it's going to be a lot of code. But it's really worth it. We reduced the hypervisor cost by more than 75%. We're better than x86 in terms of overhead for key hypervisor operations. And x86 has been optimizing their VMCS, their VMX features for a long time, a lot. So that carries some weight. We reduced the network benchmark overhead by 50%. And key value store workloads, which are really latency sensitive workloads, their overhead are reduced by more than 80%. In terms of upstreaming, the timer patches are on the list. We have a full set of core optimization patches for KVM ARM, which are ready and are working. But they're not on the list yet, but it's on the top of my to-do list. And hopefully we'll get them merged within a couple of kernel versions. And that's it. Now then I'll take questions.
So very impressive first. Second thing, so you said that, so obviously you need to keep the old 8.0 code around, right? So do you rely on static keys for switching between the two versions, or is there some magic involved?
Yeah, in the run loop there's a static key to check which version of the well switch you're going to run, and also for sort of more esoteric features like debugging and performance profiling. That is all currently pretty much handled in the old complicated well switch function. What we do now is we have a static key as well in the run loop, and only if you have either of those features enabled do you actually go and check what you need to do with the hardware. So in the common case, you don't do anything.
And would it be worthwhile to kind of push the EOS stuff of running Linux in existing EL2, so in 8.0 EL2 further? Because I mean, the numbers you showed were actually not VHE, right?
Yeah. I think that performance characteristics will be very, very close to this with real VHE hardware. There are some drawbacks of using Linux in EL2. We do slightly relax the security guarantees of software running in EL0, which is a little bit unfortunate. We can get around that, but that will have a performance cost on applications in EL0, and it will be really invasive to the kernel. So most likely not, but the patch set is available publicly for people to play with if they want. Any other questions? All right, looks like we won 8 minutes.